Okay, sorry about that. It took me a while before I noticed that audio had stopped recording. Anyway, so let's do this next one. So, same exact idea. It's just a straight up application of the ratio test. Now, notice we are dealing with a factorial here. So, recall the following useful fact about factorials. Well, not a fact, it's just how factorials are defined. So recall that by definition, n factorial is equal to n times n minus 1 factorial, right? Okay. So, in the ratio test, we have to compute this limit. So the n plus 1th term over the nth term. And it is important that it's n plus 1 over n. You can't get these flip-flopped, or else you'll end up with the... if you get these flipped upside down, then instead of getting an L less than 1, you would get an L greater than 1, and vice versa. So if you get these flipped upside down, you'll end up with exactly the opposite conclusion from what you want, or from what the correct conclusion is. So that is important. Unlike in, say, the limit comparison test, where it doesn't matter what the top and the bottom are. Okay. So, put the nth term on the bottom and the n plus 1th term on the top. So everywhere you see an n, replace it with n plus 1. Okay. Now, first off, notice that everything here is positive, clearly, so the absolute values don't have anything to do. So we may as well just drop the absolute values. Now, division of fractions is the same as multiplication by their reciprocals. Like so. Okay, and now, so we have these factorial bits, and we have these exponential bits. So let me just group those together so that it's a bit more clear what I'm about to do. So we have the factorial bits, and we have the exponential bits. Okay, so now let's see what sort of cancellation is going to happen. So, for the factorial, we're going to want to use this fact here. Because, specifically, on n plus 1 factorial, using this fact with n plus 1 instead of n yields n plus 1 times n factorial, right? Right? That's literally just this, but with n plus 1 instead of n. And that's convenient because that means that this n factorial here is going to cancel out. As for this, well, let's see. Let me do this. That makes sense, right? Instead of n plus 1 to the n plus 1, it's just n plus 1 times n plus 1 to the n. And the reason I did that is because now I have a power of n here, a power of n here, which means I can take this whole thing and raise it to a power of n. Oh, and even better, I've got an n plus 1 here and n plus 1 here. Those guys are going to cancel. So n factorials cancel, n plus 1s cancel. So all that we have left is n plus 1 over n to the power n. Okay, now it begs the question of what exactly this limit is. I mean, I can't just pull the limit underneath the exponent here, because the exponent is part of the limit, right? It's not like over here, this cube was a constant, so the limit was unaffected. But here, we certainly can't do that. So you may recall seeing an example like this in the section on L'Hopital's rule. This is an indeterminate form. So when n goes to infinity, this dude on the inside goes to 1, same as before. This dude up here goes to infinity. And 1 to the power infinity is an indeterminate form. So how do we deal with indeterminate forms like this, 1 to the power infinity? Well, what we do is we take natural logs of both sides. And then if we take a natural log, that's going to cause this exponent to move down, and that'll make things easier. So take logarithms of both sides, and then rewrite so that L'Hopital becomes applicable. Okay, so L is our limit. So the natural log of L is equal to the natural log of all of this, and natural log is a continuous function, which means that I can pull it inside the limit. So natural log of all of this junk. And indeed, the reason we would want to do this in the first place is because when we have an exponential inside the log, we can pull it out front. There, like so. That's all inside the log. Like so. Now, when n goes to infinity, this becomes log of 1. Log of 1 is 0. So this becomes an indeterminate form of the form 0 times infinity. And how do we deal with these? So we deal with indeterminate forms like this by rewriting it so that it's a fraction. So in particular, so instead of n, I'm going to write 1 over n. Okay, because now when n goes to infinity, this goes to 0, this goes to log 1, which is 0. So we get 0 over 0, which means that now L'Hopital's rule is applicable. So what's the derivative of the top? You know what? This is annoying me a little bit. Instead of n plus 1 over n, let me just divide at the top. Let me just divide by n there, so that I get 1 plus 1 over n instead. There. That way I won't have to take the quotient rule, right? Because that's ugly. Okay. So what's the derivative of the top? So since we're differentiating a logarithm, it's 1 over all of the stuff. And in the numerator, we have the derivative of the stuff. So the derivative of this is 0 plus derivative of that, which is minus 1 over n squared. Okay? Derivative of 1 over n is, once again, minus 1 over n squared. That's just the power rule. Now this is a horrifyingly ugly expression, so let's get to work on cleaning this up. Well, actually, it's actually not that bad, because the minus 1 over n square, minus 1 over n square, those guys just cancel. So really, this is all we have. And then as n goes to infinity, this goes to 0, so we just get 1. So actually, yeah, that's not bad. Okay, so the natural log of L is equal to 1. Now we need to get L by itself. So we just raise e to both sides. So wouldn't you know it, L is equal to e. Okay, so that's what our limit is in the ratio test. It's e. So what is our conclusion? Well, e is around like 2.7 something. So it's larger than 1, so that means our series diverges. Yep, so that's that. Okay, so yeah, that's the ratio test. So notice that the ratio test is going to be especially useful if you have series that have exponentials and polynomials in them, or if you have series with like factorials in them. So those are signals to you from the author that the ratio test is going to be useful. Exponentials and polynomials. Especially if you see factorials. That's the signal that you should use the ratio test, because this property right here pretty much guarantees that when you take the ratio, a whole bunch of stuff is going to cancel out. So it's going to be nice. Okay, so the reason the ratio test works is because we are systematically comparing the series that we were given to a geometric series. That's the idea, is that, yeah, we're comparing it to a geometric series. And the way that we characterized geometric series was by looking at the ratio of adjacent terms and noting that they are constant. This property is enough to characterize geometric series uniquely. Well, that's not the only way to characterize a geometric series uniquely. For instance, suppose we have a geometric series with a equals 1. And this isn't too much of a stretch because we can always just factor the number a out in the first place. So, how is this series characterized? Well, if you take the first root of this term, you get r. If you take the second root of this term, you get r. If you take the third root of this term, you get r. So and so and so. If you take the nth root of the nth term, ignoring the first one, if you take the nth root of the nth term, you get r. So, we can characterize geometric series by the property that the nth root of the nth term is a constant. Right? The nth root of the nth terms are constant. So that means that a given series is going to be eventually geometric if the nth root of the nth term is eventually constant. So that is the basis for the root test. So the nth root of the nth term is eventually constant. So that means that this guy is eventually geometric. And aside from the fact that we are now looking at a different invariant, everything else is exactly the same. The conclusions are exactly the same as in the ratio test. If this is smaller than 1, it converges absolutely. If it's larger than 1 or infinity, then it diverges. If it equals 1, then we can't say anything. And the thing with the root test is that because taking a big nth root is like really ugly, chances are like the exercises that you're going to see which use the root test are going to be really, really contrived. So like, for example, here's one where the root test is useful, but the only reason the root test is useful here is because of this big ugly power of n, which is just begging to be canceled out by that nth root. So yeah, examples using the root test are kind of contrived, but suffice to say, if you see a big ugly power of n, then that means that the author expects you to use the root test. So we compute this limit. So take the nth root of the general term. Like so. And of course, this n and this 1 over n are just begging to be cancelled by each other. The absolute values don't affect that. Absolute value is a continuous function, and that means that you can just, well, whatever. Exponents commute over absolute values, no problem. Actually, we don't even have to go that far, because all of this stuff is clearly positive in the first place. So these absolute values may as well just be parentheses for all they're going to be doing. But yeah, this n and this 1 over n cancel each other. So what is this limit? Well, the degree of the top is 1, the degree of the bottom is also 1, so the limit is just the ratio of the leading terms, so that's 2/3. So since 2/3 is smaller than 1, we conclude that the series converges absolutely. Ugh. So, there's that. Not much more to say about it. Okay, so that's it for this section. Just a couple tests. If the tests are appropriate, then yeah, they're super, super useful. And straightforward, I think. Because especially when you're using the ratio test, I mean, as long as you just do the algebra really carefully, you will find that most stuff will end up being canceled out. And then either the limit you end up with is easy, or at worst, you'll have to do like some sort of L'Hopital's rule thing to deal with it.